So in this clip, we'll discuss about spectral efficiencies. This is a number that indicate how efficient the network or mobile network use spectrum or bandwidth of transmissions. So if you look at the definitions, spectral efficiencies, or we use SE to denote spectral efficiencies, it's given by the ratio of total carrier traffic intensity. Now, if you remember from the past lectures, we can measure traffic intensities with this unit Erlang. But please note, this is carrier traffic, not offer traffic. So carrier traffic indicates the traffic that is being served by the network, but offer traffic is the traffic that is requested by the users. The two might not be the same because some of the traffic might be blocked due to limited resources. This is going to be divided by bandwidth, total bandwidth of the system. We're going to measure this in terms of megahertz, and over total area, total service area. This could be in the units of kilometer squares or meter square. Okay, so we want this spectral efficiencies to be as high as possible. That's going to indicate that we use bandwidth very efficiently. We can carry a lot of traffic given total bandwidth and given total area. Okay, now to maximize spectral efficiency, we will assume that certain quality of service is currently. For example, blocking probability might be less than some target number or target grade of service. And also SIR, which denotes signal power over interference power, right, has to be bigger than some target number. Different system has different target SIR. For example, in AMS, this is 1G system. The system requires at least 18 dB to be able to decode the signal. Okay, so how do we analyze spectral efficiencies? We'll do it through examples. Okay. So let's take a look at this example. We have a certain system that provides 395 channels for cell cluster, and this mobile system using frequency reuse factor of 7. So the n is equal to 7. We're gonna assume that the target blocking probability is 2%. That means PB has to be less than or equal to 0.02. Okay. Average holding time for a user is 2 minutes. The bandwidth is 12.5 megahertz. This bandwidth is providing 395 voice channels and 22 control channels. Now the control channel is not it's not giving a service, voice service to user. This is back office or control channels and help the system do connections with the base stations or with the mobile. Okay, so we assume that the cell radius is 2 kilometer. So the cell is sort of big. Okay, and we want to find spectral efficiencies of this system. Okay, so first we're gonna find out what is the carrier traffic intensity of this system. Okay, first we want to find the number of channels per cell. So remember, the whole system has 395 channels, and we use apply frequency reuse factor of 7. That means a cell cluster consists of seven cells which use non-overlapping channels. So each cell will be assigned on average 56.43 channels. So you take 395 divided by 7. Okay, so this is number of channels per cell. It's not whole number because this is an average. So some cell will get 56 channels, some cell will get 57 channels. Okay. Now, the number of channels of C per cell is 56.43 and the target GOS is 0.02. The question is what is the offer traffic intensity or what is the A? Okay. Now we can use the equations which gonna be tougher to find the solutions, or we can use the chart. So here we will assume Erlang B model and we're gonna use the chart. Now using the chart, we'll find an approximation instead. So we'll round the number of channels to be whole numbers, so we can look at the chart. So the number of channels is rounded to 56 and PB target blocking probability is 2%. Now from the chart we can get the A is 44 Erlang. Now what is this A, right? Remember the definitions of A is offer traffic intensity, or it's the load, right? This is per cell, right? So each cell will be requested by users in the cell, right? And the traffic intensity is 44 Erlang. Okay. Now, what is this being carried is going to be less than that because 2% will be blocked. So that means only 98% of this 44 Erlang will be carried. Okay. So the carry traffic intensity per cell is equal to 44. You take this A and you multiply with 1 minus 2%. Okay, so that's 0.98. So that's the probability of call success, right? Because 2% are being blocked, 98% are carried by the network. Okay, so 0.98 multiplied with 44, we got 43.12 Erlang. Okay, so here now we got everything we need to determine spectral efficiency. So spectral efficiency is equal to total carry traffic intensity. So each cell is it's gonna carry 43.12 Erlang. And remember, we have 7 cells in a cluster, so this is carry traffic load in a cell cluster. Okay, so we are looking at a whole cluster divided by bandwidth, right? So 12.5 megahertz, this is the total bandwidth of the system, and this is the bandwidth that is being used in a cell cluster. Okay, so bandwidth for a cell cluster, okay, it's the same as the whole system. Here has to be the areas of the 7 cells or a cell cluster. Now remember, each cell has the radius of 2 kilometer, right? And we're gonna assume that the cell looks like an hexagon. So the formula for the area of the hexagon is 2.6 multiplied with the radius raised to power of 2. Okay. So the radius is 2 kilometer, right? And there are 7 cells in the cluster. Okay. So with this, we can compute, we can obtain spectral efficiencies. It turns out to be equal to 0.33 Erlang per megahertz per kilometer square. So that means given per megahertz, per 1 megahertz per area of 1 kilometer squares, we can carry this much traffic, 0.33 Erlang. Okay. Now we are assuming that the target GOS is achieved, right? So in order to get the offer traffic, we make sure that the blocking probability is 2%. We can also look at SIR, or signal power to interference power ratio. Now we are using applying frequency, we use principle, and we can find SIR using this formula. So it's square root of 3n, right? Remember, this n is frequency reduce factor, which in this example is equal to 7. This small case n, this is the path loss exponent. We'll assume that this is in a dense area, for example in city, so the path loss exponent is gonna be toward a higher number, so we assume that this is equal to 4. I0, this is the number of closest co-channel cells, so we assume omnidirectional antennas. There's no sectorings, so signal from the base station can go everywhere in all 360 degree. So here is the number of closest co-channel cell is equal to 6. Okay, so we put in all the number and we got 21 raised to power of 2 divided by 6. Okay, so usually SIR or SNR is given in terms of dB, right? So we convert in terms of dB. Okay, so it's 18.7 dB. Okay, convert to dB scale. Okay, so this is bigger than 18 dB. For example, right, if the system we are talking about is amps, this is a little bit bigger than the requirement, which is 18 dB. So this is good. Okay, now can we do better than this? Do better means, can we increase spectral efficiency? Okay, so let's try sectoring, right? So what if we apply 120 sectoring? So that means for each cell we're gonna use antennas which cover 120 degree angles. So there are gonna be 3 sectors in a cell. Okay, now to determine traffic intensity, we're going to look at each sector. So first we're going to look at the number of channels per sector, not per cell but per sector. Okay, so the whole system has, or the whole number of channels for the whole system or for a cell cluster is 395. Each cell, you divide that number by 7. Each sector, one cell has 3 sectors, so divided by 3, or 7 multiplied by 3. Okay, so the number of channels per sector is 18.67. Again, right, it's not whole number because it's on average. So one sector might have 18 channels, and then 2 sectors will be allotted 19 channels, for example. Okay, so the number of channel is 18.67, and again blocking probability is fixed at 2%. The question is, what is the offer traffic intensity? Now we're gonna use the chart, and when we use the chart, the number of channel has to be integer, so we're gonna round this to 19. Okay, so the number that we get at the end is, it's an approximate. Okay, but I think it should be close enough to the actual answer, so we should be fine. Blocking probability is 0.02. Now from the chart we obtain that the offered traffic intensity is 11.8 Erlang. This is per sector. Okay, so offered traffic intensity is this much, but then what is being carried is going to be less because 2% are being blocked, right? Remember, where's the 2% come from? That's the probability of call blocking right there. Okay, so only 98% are being carried. So 0.98 multiplied with 11.8 Erlang. So this is per sector. Okay, now in terms of per cell, we're gonna take this number, and then each cell has 3 sectors, so multiply by 3, get 34.7 Erlang. Okay, so we come back to the same formula for spectral efficiencies. Okay, so 34.7 Erlang per cell in this scenario, multiply with 7 cells, right? So here in the numerator, this is the total carry traffic for the whole cluster, for one cell cluster, divided by bandwidth that is being used, which is 12.5 megahertz, and the area is the same. Okay. Now, if we compute this, we're gonna get spectral efficiency is equal to 0.267 Erlang per megahertz per kilometer square. Now, if you look at this number compared to what we got earlier, this is less, right? Earlier we got 0.3 Erlang per megahertz per kilometer square. This is smaller. That means this planning, right? This scenario, it's less efficient, right? Because of we got lower trunking efficiency, right? Remember, whenever we divide our resources, here is the number of channels into a smaller pools, right? So cells we further divided into 3 sectors, right? And the user in each sector cannot use a resource from different sectors, so that's gonna restrict efficiencies, right? So we got lower spectral efficiency because of lower trunking efficiency. Okay. Now, what about in terms of SIR, right? So blocking probability, that's currently at 2%. Okay. Now, with sectoring, right, the number of co-channel cell, the number of nearest co-channel cell will be cut, right? So from 6, when we use omnidirectional antennas with 120-degree angle antennas, the number of closest co-channel cells is reduced to 2. Okay, so everything else are the same. Big N is the same, 7, right? And pad lot exponents are the same. Now you compute this and convert it into dB. You see that it's equal to 33.43 dB. Okay. Now remember, if the target SIR is only 18 dB, but we got 23.43 dB, that means it's a whole lot better than the target SIR, which we don't need. We only need 18 dB. Okay, so maybe we want to lower this and make it just above 18 dB, and maybe we can increase spectral efficiency. Okay, so what can we do, right? So to reduce SIR, right? So currently we are using frequency reuse factor of 7. What if we reduce it, right? Make it lower, and hopefully the new SIR is lower but still above 18 dB. Okay, so at present we use n equal to 7. One step down, it's not going to be 6, right? Remember, n, right, has as some formula structures. For example, 7, this is coming from when we set I is equal to 2, j is equal to 1. One step down is 4, not 6, right? This is coming from I equal to 2, right? So I is the same, but we reduce j from 1 to 0. Okay, so we reduce frequency reuse factor from 7 to 4, and hopefully trunking efficiency will be bigger, and it's gonna make spectral efficiency to be a bigger number. Okay, so n is equal to 4. Let's recompute SIR. Okay, so now here n is equal to 4 instead of 7. The number of closest co-channel cells is still 2, right? We compute this, get 72, we convert into dB, we get 18.6 dB, which is okay, just a little bit above the requirement, which is 18 dB for this example. Okay, so let's compute spectral efficiency in this case. Okay, so again we want to find the number of channels per sector. Total number of channel is 395. Now since frequency reuse factor of 4, that means one cell cluster consists of 4 cells. Okay, so 395 divided by 4, that's the number of channels per cell. Further divided by 3, that's the number of channels per sector, right? It's equal to 32.92. Okay, so in order for us to use the chart, we're going to round the number of channels to be whole number, which is 33. Blocking probability is the same. Okay, so from the chart, we get that A is equal to 22.8 Erlang. And again, this is offer traffic intensity, right, per sector. Now, per cell, you take this number multiplied by 3 because there are 3 sectors in a cell. And for spectral efficiency, we want to use carry traffic, or we want to find carry traffic intensity or load per cell. So you take the previous number, multiply with 98%, because the other 2% are blocked. Okay, only 98% are carried by the network. Okay, so multiply with 0.98. Okay. So here's the carry traffic intensity per cell, right? This is per cell. To find spectral efficiency, right, we want to find total carry traffic for the whole cell cluster. So there's 4 cells per cluster. 12.5 megahertz, that's for the whole system or the cluster, right? And this is the area for one cluster, right? So instead of multiplied by 7, it's being multiplied by 4 because one cluster has 4 cells. And with this, after we compute this, we get an answer. Spectral efficiency is at the highest compared to the previous 2 scenarios. So this one is 0.52 Erlang per megahertz per kilometer square, and it satisfies all the requirement. So we can conclude, right, with this cell planning, right, with this configurations, with frequency reuse of 4, right, and we do 120 degree sectorings, or each cell is being sectored into 3 sectors. This gonna achieve better spectral efficiency. Under this requirement or constraint, right? Remember, we want blocking probability to be less than 2%. Okay, and that's okay. And we want the quality of the signal, which is being measured by SIR, to be bigger than 18 dB, which is also satisfied in this case too. Okay, so this is the end of how we can determine or analyze spectral efficiency for cellular network.